All right, last video on gases, right? Like we started with the first video, we said that there's a difference between real gas and ideal gases. Ideal gases follow the kinetic molecular theory, right? In about every aspect, which is good. And these ideal gases are much easier to deal with than real gases are. It just depends on our situation. For us, we're going to be able to talk about that. So one of the things is real gases, they do actually occupy space. Now, is that space a lot? No. All right, but because they occupy space, they are going to exert forces, right, on each other. There's no way around it. That's how chemistry works, just like we learned before. So just because they're not solids or liquids, they still exert these forces. Is it as great? No, because they're still moving around. But that idea of no loss of energy is still not always true, right? Because they experience that. So real gases, they occupy space. So they take up some of their own volume, and they do exert forces on each other. So what we want to take a look at is, well, how can we get this idea of ideal gas, right? So in order to have ideal, right, in order for them to occupy less space per what they have and not have as many forces acting on each other, we need to have high kinetic energy, and we need to spread them apart, right? So the better we do that, the more often that we can consider them ideal gases. So what we need for that is, for temperature, we need to have high temperatures, right? That's what high kinetic energy is having high temperatures to get them to spread out, basically to give them more energy to run around, right? So that's one way to do it, which is typical. The other way is to change pressure, and to change pressure is actually to lower the pressure, right? A lower pressure is going to also get them to expand further away from each other. Now, in our relative nature, we're actually doing this all the time, right? Our typical temperatures and pressures in our everyday life are close enough. These guys are spread out far enough in order to make that happen. So we actually kind of deal with ideal gases in our everyday lives most often, okay? So we have one more law that comes up that we need to know in order to go into the main part about this that we're going to talk about, is Avogadro's law, right? So Avogadro's law, now we're going to keep pressure and temperature constant, which is weird because we've always kept one of those as part of our variables. But now the one new variable is the variable of moles. So we're gonna change the number of moles, or the amount of gas in volume, and it's exactly like it seems, right? So we have this other equation where volume 1 divided by the number of moles is equal to volume 2 divided by the number of new moles, right? So if the number of moles goes up, the volume is going to go up, right? So it's like blowing into a balloon. Okay, the more molecules, the more moles you put in there, if the pressure's got to stay the same and the temperature's got to stay the same, everything else has got to go up, right? Or like breathing, right? We don't change our body temperature or pressure very much. You know, there's slightly, these laws do not happen all by themselves. That's where our next law is going to come in. But basically, we expand our chest to take in more molecules of air, and then we decrease it to exhale to get rid of them. So it just makes sense, right? The other one is, you do have a flat ball, and you might be able to heat it up to get those particles, bouncing around in there more to expand the volume. But really what most of us do is we pump it full with some more air. That's the easiest way to do it. As long as you don't put too much in and you have a decent ball, you're pretty good to go, right? So if we increase the number of molecules, it should increase the volume, which is going to make it bounce better. All right, and what all that gets us, and the reason we need this, is this idea of molar volume, right? So we've had molar mass before, which is the mass per mole of a substance. So we get that from the periodic table. We can't do that with gases, really, because gases always expand, right? So they don't have the standard density because it's all dependent on the system. So we have this gas at STP. So remember, or this molar volume at STP. So STP stands for standard temperature pressure. Standard temperature being 0 degrees Celsius, standard pressure being 1 atm. So basically 0 degrees if we're at sea level. We're never really at that, but we can create those conditions. And so what we get is we get this new equality or new ratio. So for any gas, 1 mole of any gas at STP is 22.4 liters, right? That's a lot. And so if we look at this situation, right, all these balloons are filled with different gases, right, that have different mass and stuff. But if we're saying that at STP, right, so standard temperature and pressure, there's 1 mole, they're going to take up the same amount of space because that's what they do. That's not true. If we go back to that first online lab that we did that showed the volumes that solids take up, that we didn't see that at all. Some 1 mole was at the very bottom, you know, just kind of covered the bottom, and it was heavy. The other is, you know, like the aluminum, it kind of filled up the whole thing. Gases don't do that. Okay, and that's where we get this molar volume. So this idea of if we're at STP, we can always say that. That's kind of nice. So here's the last new idea that we want for this, and this is one that we're going to use all the time, the ideal gas law. When I ask my wife what she remembers from chemistry, it's usually this, because we call it PVnRT, and you'll see why. So this is a combination of every law, including Avogadro's law. All right, and it's this. So PV equals nRT. We have pressure volume is equal to the number of moles times this constant. We're going to talk about that in a second, and T. All right, and so this is something that's given to us. Now, because we have different pressures, there's a lot of numbers, so it's not just one, and we'll see that in a second. But we still have pressure, you know, so all of our variables are in here, plus we have this constant in there. So this is a law that we're going to use quite a bit. And so I said that R value, that ideal gas constant, is based on a pressure unit. So when we look down here, there's 3 different numbers. They all mean the same thing, right? So there's liters. So our volumes have to be in liters to use this number. We have to have them moles, and we have to have it in K. That's not a big deal. The biggest one that kind of comes up sometimes is liters, like if I give you centimeters cubed or milliliters, right? We got to convert it to liters in order to use this number, but you guys are good at that. You can do it, right? So, but when you look at this number, right, it's got 4 separate units. Liters times ATMs divided by moles K. Okay, which when you really think about it, if we solve for R in the last equation, PVnRT, we would end up with those same units on the other side. And so this is based on pressure. So if we're using ATMs, we can use this number. If we're using millimeters of mercury or torr, we can use this number. If we're using kilopascals, we can use this number. Now, in reality, you could just use one of these and always convert your pressure unit to this number, or to that unit, I should say. But sometimes it's just easier, depending on the situation, to use all of these, right? The ones that these are the 3 most common. We can make up them for any of them, but these are the ones that we should have access to, right? Scary. So that, and again, I'll do some practice problems with you in a little bit, but we can also do stoichiometry, right? So we can do stoichiometry now with volumes of gas. And there's 2 ways to do it. There's an easy way where if we are at STP, we can just do this as normal. We can take our volume, use our STP, which is our 22.4 per mole, find moles, convert to moles, and we do that with our mole to mole ratio. So in this case, it would be 7 to 6 if we did that. And then if we're at STP, we can go up, right, and find a new volume. Or if we wanted to do a mass to a volume, you can do that because we know how to deal with masses. We use molar mass, and if we're at STP. The problem is when we're not at STP, right? When we can't use that 22.4. When that happens, then we have to use stoichiometry in combination with the ideal gas law, or the ideal gas formula, PVnRT. And then we kind of take a 2-step process. And I'll show you that in some practice videos. Okay? But you guys will have no problem doing that. All right. That's the last one. Hopefully you jotted down some good stuff so you have access to it. And then start taking a look at those practice problems and other example videos.